Hello everyone. I'm waiting for some more students to join. So I'll probably wait for 5 minutes, then I will be starting this session. So my screen is visible to you and my voice is clear or not? So any one of you please let me know whether my voice and screen is visible and voice is clear or not. Okay, thank you. So we will be starting the session in 2 minutes as I'm waiting for some more students to join. Okay, so I will be starting the session. So, hello everyone. My name is Imanshi Singh. I am from Department of Mathematics, IIT Jodhpur. Currently, I am pursuing my PhD here in broad area of probability and statistics. So, today we will be discussing a brief. I will be giving you a brief recap about the week 10 lectures, and then we will be discussing some of the questions based upon the concepts which we have already studied in week 10 lectures. So I will be starting with the recap. So in week 10 lectures we already know from the previous lectures about the what is a statistic basically. So statistic is a function of random sample. So if I have x1 x2 xn a random sample, then any function of that random sample we will be calling it as a statistic. Now what is sufficient statistic? So basically if I have a random sample x1 x2 xn, then and it is taken so it is taken from the population which is following the distribution p theta, then a statistic T is said to be sufficient if the conditional distribution of x1, x2, xn given T is equals to T is independent of theta for almost all t. So if the conditional distribution is independent of theta, then independent of the parameter, then we will say that t is a sufficient statistic. So some of the example which have already been done in the week 10 lectures. And also, so the conditional, always finding out the conditional distribution is not that easy task. So we have a different method to find the sufficient statistic, which is called the Neyman Fisher factorization theorem. So if I will write the joint density of the x1 x2 xn random sample, then if this joint density can be written as a function of tx comma theta multiplied by a function of x, here x is nothing but the random vector x1 x2 xn, then we'll say that this t is sufficient. Okay, so what I can do, I can just take the product of all the densities or the joint density x1 x2 xn, and if I can write this in this form, then the corresponding t, we will call this t as sufficient statistics. So this sufficient statistics have this alternative definition, or an alternative way by which we can also find the sufficient statistic t apart from this conditional distribution. Now, why this sufficient statistic is important? Actually, this helps in data reduction. So, if we have the knowledge of the sufficient statistic, by that knowledge, we can again construct the random samples. So, if I have random sample and if t is a sufficient statistics, and then if I know that the t that, for example, let t is equals to summation xi. For example, let us consider that this is sufficient statistic. So by the knowledge of this t, I can again generate the random sample x1, x2, xn. So in that case, I do not need to or do not need to have this data stored on in my device. I only need to store this t, so that because t is sufficient statistic for the distribution. So basically it helps in data reduction. So that's why this notion is important. The notion of sufficient statistic is important. So apart from sufficient statistic, there is a property of sufficient statistic, that is completeness. So first of all, we'll discuss what we mean by completeness. So if I have a family of probability distribution p, so here this p contains all the p theta, theta and theta. Okay, so I will say that this family of probability distribution is complete if expected value of gx is equals to 0, implies that probability gx is equals to 0 is 1. So basically any unbiased estimator of 0. So since expected value of gx is 0, so basically gx is unbiased estimator of 0. So if gx is an unbiased estimator of 0, this will imply that gx is nothing but a 0. So this is random variable which is almost everywhere 0. Okay, so then we will say that this family is complete. Okay, now when a sufficient statistic will be complete, so sufficient statistic is basically a function of random sample. By this probability distribution, I can find out the family of probability distribution of the sufficient statistics. So if the family of probability distribution of the sufficient statistic is complete, then we will say that the sufficient statistic t is complete. So why this completeness, the notion of completeness for the sufficient statistic is important? Actually, this helps in constructing the uniformly minimum variance unbiased estimators, so which we will be discussing in next theorems. So apart from this, if I consider this exponential family, so the majority of the distribution which we have discussed, uh, they belongs to this exponential family. So in broad sense, if I consider this exponential family, and I write this exponential, so this is basically a family of probability distribution where the density is given as this form, that is c theta hx exponential of summation I going from 1 to n theta I ti x. So this is basically so. Any question? Okay, is there any question? Is my voice is clear to you?
Yes, ma'am.
Okay. Okay. So yeah, I was saying that exponential family. So this the density is given in this form. So we'll call a family where the densities are of this form. We'll call that family to be the exponential family, and actually this is key here. Okay, so this exponential family, and if we can see through the density only, if I can see that the density, if by Neyman this factorization theorem, here we have studied this factorization theorem. So by this factorization theorem, we can say that this TIs are the sufficient statistics basically. So T1, T2, TK is a sufficient statistic for this family. Now for this exponential family, we have result that this sufficient statistic is complete. Okay, so when it is complete, given that this theta, which is the range of the parameter theta 1, theta 2, theta k, when it contains a k dimensional rectangle, then we'll say that this sufficient statistic is basically a complete sufficient statistics. So this complete sufficient statistic plays a very major role in constructing the UMVV, that is uniformly minimum variance unbiased estimators, which I will be discussing in next two theorems. So first of all, uh, we have already studied this notion of UMVV. So what is UMVV basically? It is uniformly minimum variance unbiased estimator. So if I consider a class of unbiased estimators, so if so UMVV will be that estimator which will be having the minimum variance among all of them. Okay, so we will consider that estimator to be a good estimator in order to estimate the parameter. So how can we find out this UMVV? So first of all, there is a method of lower bound. So if Tx is an unbiased estimator of theta, then variance of Tx is greater than is equals to 1 upon n into I theta. So basically this variance of Tx will always be greater than this quantity. It can be equal to this quantity, but it will be always be greater than this quantity. So basically the minimum variance unbiased estimator will be having this variance 1 upon n I theta. If some of the estimator have this variance, then we'll say that it is a UMVV. Okay, so here this I theta is nothing but expected value of del over del theta of log f theta x whole square. So this we call it as a Fisher information. Okay, so this is one of the method by which if I can find out any of the estimator which attains this bound, then I'll say that this is UMVV. Okay, there may be a possibility that it may not be attain the bound, but if it attains the bound, I will say that it is UMVV. Okay, so this is one of the method to find out the lower bound. Now another method is Rao Blackwell Lemon Shafi approach. So what it is basically, so I will be discussing that. Now first of all, a Rao Blackwell theorem is there. So what it says, so if I have if I have an unbiased estimator of g theta, that is dx, okay, and t is the sufficient statistic, then but with the help of this sufficient statistics I can I can construct another estimator of g theta which have less variance. So basically what am I doing, that I'm constructing an ht, that is function of sufficient statistics, which is equals to expected value of dx given t. So this is basically again a function of t. Okay, now this is unbiased for g theta again, and variance of ht, the variance of this new constructed estimator will be less than or equals to the variance of dx. So basically this is better than dx. Okay, so by this theorem, we came to know that if I have any unbiased estimator of g theta, then with the help of sufficient statistic, I can construct another estimator of g theta which has lesser variance. Okay, so now with the use of this theorem, we have again another theorem when t is a complete sufficient statistic. So that is Lyman-Shafi theorem. This is very important in order to construct the UMVV. So if T is a complete sufficient statistic, then HT is UMVV for its expectation. So basically what it is saying, that if T is complete, so basically this is complete sufficient statistic, then HT, So if I consider expected value of ht to be g theta, let us consider, then ht is an unbiased estimator of g theta. Okay, this implies if t is complete that ht is umvue for g theta. So basically what I need to construct, I need to construct only an unbiased estimator of g theta in order to get the umvu. So that unbiased estimator will be a function of complete sufficient statistic. Then I will say that it is of minimum variance. So by this theorem and by this notion of complete sufficient statistic, I can construct a umvu very easily, because only I need to construct the unbiased estimator for g theta, that will be the umvu. Okay, so this is the importance for completeness property of the sufficient statistic. So I hope this thing is clear. I will be explaining this by one example also in the problems when I will be discussing. So everything is fine until now. Are you guys with me?
Yes, ma'am.
Okay. Uh, okay. So I will be going towards the interval estimation. Now, apart from all these things, we have already studied the point estimation, where we were finding out the value of the estimator, which is fixed. Now we will go towards the interval estimation. So what is the interval estimation basically? So we will construct a confidence interval. So what is confidence interval? So if I have a random variable with distribution p theta, and x1 x2 xn are the random sample from this distribution, and let us consider that t1x and t2x be two statistics. Okay, so these are two statistics such that the probability of t1x less than or equals to g, so that probability that g theta is between t1x and t2x is 1 minus alpha. So this holds. Then if the random sample x, so this is observed, so this is the realized value. So if this is observed, then we'll say that this T1 x bar comma T2 x bar is 100 into 1 minus alpha percent confidence interval for g theta. So if the probability of g theta lying between T1x and T2x is 1 minus alpha, then we'll say that this g theta will lie in this interval T1 x bar, T1 x and T2x, is the probability that it will lie in this interval is 100 into 1 minus alpha percent probability. Okay, so or we can say that the probability for this occurrence is 1 minus alpha. So we'll say that this is a confidence interval with 100 into 1 minus alpha percent. Okay, so this way we'll find out the confidence interval. Now further we'll only considering that the random sample of the population is from the normal distribution, and we will be constructing the confidence intervals on the basis of the knowledge of the parameters. Okay, so what we'll be considering first of all, so if I consider that x1 x2 xn are coming from the normal mu comma sigma square. Now if I want to construct the confidence interval for mu, okay, and we have two conditions, that if I want to construct confidence interval for mu, then I have two cases, that whether the variance is known or the variances are known. So if the variance is known, the confidence interval will be this: x bar minus z alpha by 2 sigma by root n, comma x bar plus z alpha by 2 sigma by root n, where z alpha by 2 is nothing but, so if I consider this standard normal curve, then this is point z alpha by 2, where the area in the right hand side is alpha by 2. Okay, so this z alpha by 2 is this point. Okay, and sigma is the standard deviation here, and n is the size of the random sample, and x bar is the sample mean. And if sigma square is not known, then in that case I will be having this confidence interval by replacing this z to t. Here I'm having this t, so this is coming from the t distribution. Okay, alpha by 2 at n minus 1 degrees of freedom. So x bar minus t alpha by 2 n minus 1 s by root n, x bar plus, so here it is t alpha by 2 n minus 1 s by root n. So here s is the sample variance, because we do not know we do not know the population variance. So we will be calculating the sample variance from the sample we have, x1 x2 xn. Okay, so this is the these are the confidence intervals for mu. Now if I want to construct a confidence interval for sigma square, then I have again two conditions, that mu is known or mu is unknown. So if mu is known, then this will be the confidence interval where we have the appearance of the chi-square distribution. So we will be finding out these values using the chi-square table. And if mu is unknown, then again I have this n minus 1 s square divided by this chi-square alpha by 2 n minus 1, and n minus 1 s square divided by chi-square 1 minus alpha by 2 n minus 1. So we will be finding out these values from the chi-square tables. Now, now if I have two normal populations, okay, here until here I have only one normal population. Now, if I have two normal population and I'm interested in order to find out the difference of the mean, the confidence interval for this difference of the means. Okay, so let me consider that x1, x2, xm are coming from normal mu1 comma sigma 1 square, and this y1 y2 yn are coming from normal mu2 comma sigma 2 square. So I have two normal populations. Then uh, the confidence interval for mu1 minus mu2 will have three conditions basically. So if sigma 1 square and sigma 2 square both are known, apart from this, if both are unknown and both are equal, and the third condition will be both are unequal and are unknown. Okay, so if both are known, then we will be having this confidence interval. Here z alpha by 2 again is standard normal, it is coming from standard normal table. And here if both are equal and known, then in that case we will be having this appearance of this sp, we call it as a pooled sample variance. So this formula for this sp is given as m minus 1 s1 square plus n minus 1 s2 square divided by m plus n minus 2. Okay, here m and n are the sample sizes from both the population. S1 square is a sample variance, and S2 square is a sample variant for the random variable x and y. And here again this t alpha by 2 m plus n minus 2, it will come from the t distribution table. Okay, now if both are unknown and both are unequal, then in that case we have this approximate confidence interval. So here we have this appearance of this t alpha by 2 nu, where nu is the degrees of freedom, and we will be finding this degrees of freedom by using this formula. Now this may not be like a integer, or I can say it may not be a natural number, so we will round it off to the nearest integer. Okay, so these are the confidence interval for the mu1 minus mu2. Okay, the difference of the means. Now apart from this, we have for example, I have paired observations like x1, x2, x up till xn, yn, which are following the bivariate normal distribution with mu1, mu2, sigma 1 square, sigma 2 square, and rho. Then in that case, if I'm interested in the difference of xi minus yi, that is di. So this is the difference basically, and I want to find out the confidence interval for mu1 minus mu2. Okay, so that confidence interval will be this d bar. So d bar is basically, so if I will consider this di's, and the mean of the di's will be the d bar minus sd divided by root n t alpha by 2 n minus 1. Here this sd will be the standard deviation for this observation. Okay, so this is for the difference of the means. Okay, now if I want to consider the ratio of the variances, sigma 1 square divided by sigma 2 square. So I have two conditions again, that mu1 and mu2 both are known or both are unknown. So if both are known, then we will be having this appearance of this f distribution. Now here this is f distribution, this f 1 minus alpha by 2 n comma m. So we will be finding these values from the f table. And again, if mu1 and mu2 both are unknown, then we will be having this distribution. So s1 square will be the sample variance for the population for this x1, x2, xn, and s2 square will be the sample variance for y1, y2, yn, and here f will come from the f distribution table. Okay, so these are the confidence interval for the various parameters which we may be interested. So we will be considering questions based upon all these concepts. So if there is any doubt regarding these regarding these concepts, then you may ask. Otherwise, I will be moving forward towards the questions. So everything is okay till now? Okay. So at least response, because at least I know that whether you people are there with me or not. Okay, so this is the first problem. So we have x1, x2, xn are the random sample from from normal 0 comma sigma square. So here the mean is 0 and the variance is sigma square. And consider this t, which is 1 upon n under root pi by 2 summation I going from 1 to n mod of xi. Okay. Now we need to check whether T is unbiased and consistent estimator for sigma or not. So for unbiasedness, we will be finding out the expected value of this T. So first of all, let me consider this expected value of T. So I am first interested in unbiasedness of T. Okay. So let us consider this expected value of T. So expected value of T will be, because this is just a scale, so this is just like number, so it will come outside 1 upon n under root pi by 2 summation I going from 1 to n. Now expectation will go by the linearity property, it will go inside, so it will be expected value of mod of xi. Now each xi is normal 0 comma sigma square, so we just need to find out what it will be the expected value of xi, or I can say what will be the expected value of x if x is a normal 0 comma square. So first of all we'll find out. So let x follows normal 0 comma sigma square, then what will be the expected value of mod x? So what it will be? So it will be nothing but, so it will be integral of mod x into the density. So density of x is, so it is normal 0 comma sigma square, so density will be 1 upon under root 2 pi sigma square exponential of minus 1 by 2 x square by sigma square, because here mu is 0, dx, and x is going from minus infinity to infinity. So this will be the expression for the expected value of mod x. Now I can see that this function in the integral, so this function is an even function. So if I replace this x with minus x, the function will be same. So this is an even function, so we can write this as twice of integral 0 to infinity uh, mod x 1 upon under root 2 pi sigma square e to the power minus 1 upon 2 x square by sigma square dx. Now you see here that the range of x is positive always. So mod x, or I can write x or mod x, because x is always positive. So mod x will be x. So I am taking this constant term outside under root 2 pi sigma square. So this is integral 0 to infinity x into e to the power minus x square by 2 sigma square dx. So further I will solve this integral. So I'll take x by sigma to be t. So it will be, or I can take x square by sigma square to be t, or x square by 2 sigma square to be t. Then, so this will be 2x dx is equals to 2 sigma square dt, or I can say x dx is equals to sigma square dt. So I'll put the values here. So this is equals to, so it is 1 upon sigma here under root of 2 upon pi here, integral 0 to infinity, and the limits will be same, because when x is 0 t will be 0, x is infinite t will also go towards the infinite. So here this x dx will be sigma square dt, so here sigma square will come, and e to the power minus t we will be having, and this is dt. Okay. So this 1 sigma square will get cancelled by this sigma, so it will be so this will be equals to sigma under root 2 upon pi and integral 0 to infinite, and it will be e to the power minus t dt. So it is e to the power minus t dt. So if I'll find out the integral of this thing, so it will be again minus e to the power minus t 0 to infinity. So upper limit it will go towards the 0 and lower limit it will go towards the 1, and the negative sign will get positive. So it will be sigma under root 2 upon pi. So this is basically the expected value of mod x. Okay, so this is expected value of mod x. So I will be putting this value here. So expected value of mod xi will be the same because all of them are standard. So normal with 0 comma sigma square. So expected value of t is equals to, so it is 1 upon n under root. So it is 1 upon n under root pi by 2, summing I going from 1 to n. So it will be sigma under root 2 upon pi. Now this is a constant, so it will come outside, and this will be summation over 1, so that will be n. So it will be sigma under root 2 upon pi n, and this will be here n, so it will get cancelled. So this will get cancelled and this n will get cancelled, so it will be sigma. So this implies that t is an unbiased estimator of sigma, since we are getting that expected value of t is sigma. Now in order to find out that whether it is a consistent estimator or not, we need to check whether variance of t is going towards 0 or not as n tends to infinity. So for that we will be finding out the variance of t also. Okay, so variance of t will be what? So variance, now okay, first let me write. So now consistency of t. Okay, so for that I will be having this I will be finding out this variance of t. So since we have this expression here, so variance if I will apply, then this quantity will be the square of this quantity will come outside. So it will be 1 upon n square pi by 2. Okay, and this is a random sample, so we are considering that these are independent. So the variance of, so this will be summation I going from 1 to n variance of xi. So this will be summation I going from 1 to n variance of mod of xi. Okay, so now we are interested in variance of mod xi. So what will be the variance of, so if x so if x follows normal 0 comma sigma square, okay, then so we are interested in variance of mod x. So that will be what? So variance of mod x will be what? Expected value of mod x square minus expected value of mod x whole square. Okay, so I can write it as expected value of mod x minus expected value of mod x whole square. Okay, so okay, so here if I consider x by sigma, so x by sigma will be following normal standard normal, and so it will be standard normal following standard normal distribution, and x square by sigma square will follow chi square with 1 degrees of freedom. We have already studied this, as square of a standard normal distribution follows a chi square distribution, so it will be chi square distribution. So what I'll do, I'll just take sigma square here and and divided by this sigma square. Okay, so this will be sigma square into expected value of mod of x by sigma, I can write minus expected value of, so expected value of mod x I already know, so it will be expected value of mod x is sigma into under root 2 upon pi. Sigma into under root 2 upon pi. So let me consider it in another way. You just forget about it. So let me go by the basic method only. So I already know this expected value of mod x. I need to calculate the expected value of mod x square. So this is expected value of mod x square. So it will be integral of mod x square into what will be the density of a standard normal distribution. So that will be 1 upon under root 2 pi sigma square e to the power minus x square by 2 sigma square dx, and it is going from minus infinity to infinity. Now again I can do the same thing because it is again an even function, so I can find out this to be twice of minus infinity to infinity. So it will be 0 to infinity because it is an even function. So it will be 0 to infinity. This will be x square and it will come outside under root 2 pi sigma square. So it will be x square e to the power minus x square by 2 sigma square dx. Okay, now again we have this form. Then I can just take x square by 2 square again as t, and I will just reformulate this in the form of t, and I can apply the formula for the gamma function. Okay, so the result I will be getting. So let me add one more. So from that substitution and all those things, we will be getting this expected value of mod x square. You can find out it. You can find out this. So expected value of mod x square will be. So it will of the form. I can also write that it will be of the form. So by taking uh, x square by 2 sigma square as t. So this will be of the form 0 to infinity. So it will be of the form t to the power 3 by 2 minus 1 and e to the power minus t dt. And here it will be 2 and 2 root 2 of divided by root 2. So it will get cancelled root 2 pi, and here I will be having this sigma square dt. Okay, so this will get cancelled, and we will be left with. So it will be like so. This is the gamma function. So the value will be gamma 3 by 2, and here I will be getting this 2 outside and this sigma square outside. Okay, so it will be 2 sigma square into 1 by 2 gamma 1 by 2. So I'm also having this under root pi here. Under root pi, under root pi. So it will be under root 2 pi. So sigma square under root 2 pi, this 2 will get cancelled upon under root pi. So it will be wait a minute. So let me write it again. So here if this x square by 2 sigma square is t. Okay, so then 2x dx divided by 2 sigma square will be dt. So this 2 will get cancelled and x dx will be sigma square dt. Okay, so this equation will become, I'm solving it. So this will be under root 2 upon pi already. So, or I can say 2 upon under root 2 pi sigma square integral 0 to infinite. And here I am having this x square. So I'll take x here and one of the x dx. So there will be one x dx. So that x dx will be sigma square dt. So sigma square dt here. and this will be e to the power minus t. So it will be e to the power minus t. So here again, what I will do, I will be this under root 2 pi sigma square integral 0 to infinite. So here in place of x, what I can write, x will be, since x square by 2 sigma square is t, so x will be, so this will be 2 sigma square t, and this will be under root of this thing. So this will be under root of 2. So sigma square will be sigma and t to the power 1 by 2. And here already I have this sigma square. So this will be sigma square e to the power minus t dt. So I will be having sigma cube here, and in the denominator we have 1 sigma. So this is 2 root 2 divided by under root 2 pi. This sigma will get cancelled and there will be sigma square here, and integral 0 to infinite t. So 1 by 2 can be written as 3 by 2 minus 1 into e to the power minus t dt. So this function will be gamma function. It will give gamma 3 by 2. So it will be gamma 3 by 2. So which will be equal to 2 root 2 divided by under root 2 pi sigma square, and this will be 1 by 2 gamma 1 by 2, which is under root 2 pi. Okay, so this will get cancelled and this will get cancelled. So it will be okay, wait. So this is not under root 2 pi. Yeah, I'm making a mistake here. So gamma 1 by 2, gamma 1 by 2 is under root pi. Yeah. So it is under root pi here. So this will be under root pi here. So this under root 2 pi will whole get cancelled and it will be sigma square. Let me write it again. So it will be 2 root 2 divided by under root 2 pi sigma square, and it will be 1 by 2. Gamma 1 by 2 will be under root pi. Okay. So now this under root 2 pi and this under root 2 pi will get cancelled, and this 2 will get cancelled, and it will be sigma square. So this will be the expected value of mod x square. Okay. Now what we need to calculate actually, so we need to calculate this variance. So variance of mod x. So variance of mod x will be equals to expected value of mod x square, which we have already calculated, that is sigma square, and minus expected value of mod x square. Now expected value of mod x we have calculated as sigma into under root 2 upon pi. So it will be minus sigma into under root 2 upon pi whole square. So it will be sigma square minus 2 upon pi sigma square. So it will be pi minus 2 upon pi into sigma square. So this is variance of mod x. Now we will be going towards this thing. So it will be variance of t will be, so variance of t is equals to 1 upon n square pi by 2. So 1 upon n square pi by 2 summing I going from 1 to n, and here we have variance of mod xi, so we will put this value. So pi minus 2 upon pi into sigma square. So now this is a constant, so it will come outside, and this will be 1 upon n square pi by 2, and this is pi minus 2 upon pi into sigma square, and the summation will go, so it will be n. So this n will get cancelled, this pi will get cancelled, so it will be pi minus 2 upon 2 sigma square by n, which will go towards 0 as n goes to infinity. So this implies that t is a consistent estimator. Okay, now what next in the question? So also find out the Cramer-Rao lower bound for the variance for sigma. So we need to find the Cramer-Rao lower bound. Okay, so Cramer-Rao lower bound. So variance of t, by that we have already discussed that variance of t will be greater than equals to 1 upon n into I of sigma. Since t is an unbiased estimator of sigma and variance of this t is less than infinite, so the variance of t will be this n into 1 upon n into I theta. So this is basically the Cramer-Rao lower bound. So we will be finding out this lower bound. So what is this lower bound? So what is this I sigma? So I sigma is expected value of del over del sigma, not square. We are talking about only the sigma. So it will be del over del sigma of log f x theta, or I can say we are talking about here sigma. So over theta is sigma only. So it will be sigma. Okay, so we'll calculate, so square. So we'll calculate first the del sigma, del over del sigma of log f x sigma. So what we have this, so del over del sigma of log. So what we have the density, so density is 1 upon under root 2 pi sigma square e to the power minus x square by 2 sigma square. So this is the density. Now when I will be taking the log for this expression, so this will be for under root 2 pi, it will be minus 1 upon 2 log 2 pi. Okay, and this is sigma, so it will be uh, minus log sigma, and this will be minus x square by 2 sigma square, log e will be 1, so it will be this. So when I differentiate it with respect to sigma, so this quantity will be 0 as there is no sigma, and this quantity will be 1 upon sigma, and this quantity will be minus x square by 2, and when I differentiate this with respect to sigma, it will be minus 2 upon sigma cube we have. Okay, so this 2 will get cancelled and this will become plus, so it will be x square by sigma cube minus 1 upon sigma, or I can say this x square I'm taking as capital because we are, so this is basically a random variable. Okay, so we need to calculate the expected value of this square. So expected value, so I sigma will be expected value of this square of this term. So x square upon sigma cube minus 1 upon sigma whole square. Okay, if I take 1 upon sigma outside, 1 upon sigma outside, so 1 upon sigma I'm taking outside here, so the in the whole term it will come sigma square. So expected value of x square by sigma square minus 1. Now see, this x follows normal 0 comma sigma square. ठीक? This implies that x upon sigma follows normal 0 comma 1. Okay, so which will imply that x square by sigma square follows chi square with 1 degrees of freedom. Okay, which implies that expected value, so it is whole square here, expected value of x square by sigma square is equals to the degrees of freedom, so that will be 1, and variance of x square by sigma square will be the twice of degrees of freedom, so it will be 2. Okay, now by this expression we can see that this is expected value of x square by sigma square minus 1. So this is basically expected value of x square by sigma square minus of expected value of x square by sigma square. So I sigma is equals to 1 upon, we can write this as expected value of x square by sigma square minus expected value of x square by sigma square whole square. Okay, because here it is 1. So this is basically the variance of x square by sigma square. Okay, so which implies that I theta, or I can say that I sigma is equals to 1 upon sigma square into variance of x square by sigma square. Now variance of x, this is variance of x square by sigma square, so that is 2. So this will be 2 by sigma square. Okay, one of the other way to find out this thing by taking the square of all the terms and take the expectation with respect to the normal random variable, normal density, then also you can find out, but this is a short way to find out by making this as a chi-square distribution. Okay, so this I sigma will be A. This will be the Kramer Rao lower bound. Okay, and also we know that variance of t. So what was the variance of t we have calculated? So variance of t we have calculated. So variance of t is this, pi minus 2 by 2 into sigma square by n. Pi minus 2 by 2 into sigma square by n. Okay, so so this is the variance of t, and this is the Kramer-Rao lower bound. Okay. Oh, okay. This is okay. Sorry. So this is we have called calculated the Fisher information. So the Kramer-Rao bound will be, so Kramer-Rao bound bound will be 1 upon n into I theta. So I theta will be 2 upon sigma square. So it will be like this. So it will be sigma square by 2n. Okay. So we can see that this variance of t. So this is pi minus 2 into, so pi minus 2 will be a greater than 1 quantity. So this quantity is greater than is equals to sigma square by 2n. So this implies that t does not attain the bound. Okay. So here we have what we have done. We have first seen that uh, what is so whether that the t is consistent estimator or not, whether it is a unbiased estimator or not. Then after that we have find out that what will be the Kramer-Rao bound for it, and we have checked that whether that estimator is attaining the Kramer-Rao bound or not. So where it is not attaining the Kramer-Rao bound, it is greater than the variance. It is greater than the Kramer-Rao bound. The variance of t is greater than or equals to sigma square by 2n. By this expression we can see. So it is not attaining the bound. So is this clear? Is this clear to you all? Okay. So I will be moving forward towards the next question. So here we have that x1, x2, xn are the random sample from the normal population with mean 0 and variance theta. So here this variance is theta. It is not sigma square here. We are giving that variance is theta here. Okay. Then find out the uniformly minimum variance unbiased estimator for theta square. We need to find out the minimum variance for theta square. Okay. Now we know that. Okay, let me start from the density onwards. Okay, so if I write the density of x1 up till xn theta, so since they are random sample, so it will be product of the density. So it will be of the form 1 upon under root 2 pi sigma square to the power n into e to the power minus 1 upon 2 summation I going from 1 to n xi square by sigma square. So we do not have sigma square here, we have theta here. We have theta here, so we'll write theta here. Okay. So this is basically the density form. So by this, by factorization theorem, we can say that, so by factorization theorem, we can say that summation xi square I going from 1 to n is sufficient statistic. Okay, now, so this is a sufficient statistic. Again, we can also say that this is exponential family. Okay, and here we have 1 upon theta. So 1 upon theta. Now theta is a variance, so it belongs to like it is greater than equals to 0. So 1 upon theta is also, so this so, or I can consider minus 1 upon theta. So this will be the theta i's for this. So minus 1 upon theta belongs to minus infinity to 0. So this, the range is containing the one dimensional rectangle, or I can say the open set. We are having the range as an open set. So which implies, okay, so this implies summation xi square I going from 1 to n, or I can make it as a capital Xi square. So capital Xi square is complete sufficient statistics. Statistic. Okay, so this is complete sufficient statistic. So and for what, so this is an estimator, so we already know that so if I consider so this is, okay, so this is a complete sufficient statistic. Now what I need to find out in the question, I need to find out the uniformly minimum variance unbiased estimator for theta square. Okay, so first of all we'll see that for what is, so x as, so xi follows normal 0 comma theta. So this is the distribution for xi. Okay, so this implies xi by theta. So this is the standard deviation. Okay, so this is the variance law. So xi by under root of theta. This follows normal 0 comma 1. So this will be a standard normal random variable, which implies that xi square by theta. Okay, this follows chi square with 1 degrees of freedom. Okay, so this implies that summation I going from 1 to n xi square by theta. Okay, this follows chi square with n degrees of freedom. Okay, so expected value of summation I going from 1 to n xi square by theta. So this will be equals to the degrees of freedom, which is n. Okay, so from here we can see, so which will imply, so if I take this theta there and n here, so this implies that expected value of 1 upon n summation xi square is equals to theta I going from 1 to n. So which implies that 1 upon n summation xi square I going from 1 to n is unbiased estimator for theta. So this is for the variance, but we are interested in theta. But we are interested in theta square. Okay, so what we will consider for that? Okay, so we'll consider this variance of 1 upon okay, now xi square, so this xi square by theta follows the chi square n. So we'll consider this variance of this quantity. So variance of this quantity will be variance of summation I going from 1 to n xi square by theta. So variance of this will be 2n because it follows the chi square distribution with n degrees of freedom. So what will be the variance? So it will be expected value of summation I going from 1 to n xi square by theta whole square minus expected value of summation xi square by theta whole square is equal to 2n. Now we already know that expected value of summation xi square by theta is what? So this is, so expected value of this thing is n already. So we'll put this value n here, so it will be n square. So this implies that expected value of what it is 1 upon theta square summation xi square whole square is equals to 2n, and this will be n here and is n square, so it will be plus n square. Okay, so this implies that expected value of, so what I will do, I'll take this 2n plus n square here in the denominator, so it will be 1 upon 2 plus n, I taken n as common, I going from 1 to n xi square whole square is equals to theta square. So which implies that this 1 upon n into 2 plus n summation xi square whole square, I going from 1 to n, is unbiased estimator for theta square. But since it is a or I can say it, since it is based upon complete sufficient statistic. Now it is based upon the complete sufficient statistics. So this implies that 1 upon n into 2 plus n summation xi square whole square, I going from 1 to n, is UMVUE for theta square. So this is basically the role of the complete sufficient statistic, that if that our estimator is based upon the complete sufficient statistic and it is unbiased, then it will be of minimum variance, which we have already studied in the result. So we have used that result in this example in order to find out the UMVUE for theta square. Again, if I say about theta, then for theta the unbiased estimator was this one. So for theta, this is an unbiased estimator and it is based upon the complete sufficient statistic. So it will be UMVE also. So for theta, it will be the UMVE, and for theta square, this estimator will be the uniformly minimum variance unbiased estimator. So is these things are clear to you? We are using majorly the results, and we are doing the things here and there using the chi-square distribution and all those things. So is this clear? Okay. So now we have talked about the statistics and sufficient statistics and complete sufficient statistics. So we will be talking now about the confidence intervals. Okay. So here in the design of wheel of a car, random variable of interest is displacement. So we are interested in the displacement of the constant velocity joints. Okay. So in 16 runs of the experiment, so basically we are considering n to be 16. So in 16 runs of the experiment, the following observations are obtained. So these observations are obtained. So these are displacements basically. So find a 99% confidence interval for the standard deviation. Now we need to find 99% confidence interval for sigma. Okay, now we can see here that uh, mu is unknown. The mean of the population is not given. Okay, so we'll apply the formula where t distribution arises. So mu is unknown, so we'll calculate the x bar. Okay, now so first of all, let me write what will be the confidence interval. So first of all, we have this 99% confidence interval. So this implies that alpha is 0.01. Okay. So how am I writing it? So 99% interval means 1 minus alpha is 0.99, which implies alpha is 0.01. Okay. So the confidence interval for sigma is, so it will be x bar minus, so I will be writing it, it is based upon the, so yeah, so it will be no, not this. So it will be, since the standard deviation is unknown, sorry, the variance is, we are using the finding out the the standard deviation. So we are using this n minus 1 s square by sigma square follows chi square with n minus 1 degrees of freedom. So here it will be n minus 1 s square by chi square with alpha by 2 comma n minus 1 comma n minus 1 into s square by chi square 1 minus alpha by 2 into n minus 1. So what where from where I'm using it, I've already explained it here. Yeah, so if the mean is unknown here, so the confidence interval for sigma square is this. So for sigma, it will we will be taking the under root of both the things. So mu is unknown, so we will be using this. Okay. So we'll take the under root of this quantity. Okay, so here we are interested. So we know that what is n is 16. So what is s square? So s square will be 1 upon n minus 1 summation xi minus x bar whole square. I going from 1 to n. Okay, so it will be 1 upon 15 summation I going from 1 to n xi minus x bar whole square. So just calculate what x bar is for these values. What x bar is? What is this x bar? So anybody is calculating? Anybody from you is calculating x bar? My voice is clear to you? Please respond.
Yes, ma'am.
Okay. So you've calculated this x bar. I should write it myself. You only need to sum it up and divide it by 16.
Calculating, ma'am.
Okay, so what is the value of x bar?
Just a minute, ma'am. 3.2125, ma'am.
Is 3.212. I will
25.
consider this. Okay, so it will be 3.2125. So by using this x bar, you can calculate this s square. Okay, so s square, we'll just subtract each value from this quantity and we'll square and sum it up and divide it by 15. So you just do the calculation. I'm writing it here, the value of this. So it is coming out to be 1.561. Okay, so this is s square we have. So what we will do, we know now s square, we know this n. We do not know this chi square alpha by 2 n minus 1. So chi square. So what is alpha? Alpha here is 0.01. So alpha by 2 will be 0.005. Okay, and so we will be writing it as chi square. Now this is alpha by 2, so alpha by 2 is 0.005 comma n minus 1. N minus 1 is 15. So we need to find out this value, and again what is the second one? It is 1 minus alpha by 2. So alpha by 2 is 0.005, so 1 minus alpha by 2 will be 0.995. Okay, so this is 0.995 comma 15. So now we will find out this by using the chi-square table. So how will be doing that? So I am, so we have this alpha value 0.005. So we have this chi-square table where alpha value is 0.005. So this will be the 0.005 value, and we have degrees of freedom to be 15. So it will be this value. So it will be 32.801. Okay, so it will be 32.801. Again, we have chi-square 0.995 at 15 degrees of freedom. So 0.995. So at 15 degrees of freedom, we have 4.601. Okay, so we will be writing these values 4.601. Now we'll substitute the values here in this formula. So it will be, so confidence interval will be, so it will be square root of 15 into s square. So it will be square root of 15 into, what is s square? We have 1.561 divided by chi square at alpha by 2 n minus 1 degrees of freedom. So that will be 32.801. 32.801, and under root of 15 into again 1.561 divided by this value 4.601. So this will be the confidence interval. When you evaluate it, the values will be, so the values will be 0.
0.0.8448.
Yeah,
0.8448,
yeah,
2.2559.
2.2559. It's correct. So this will be the confidence interval. So it will be the how much percent? 99 uh, percent. So this is the 99% confidence interval for sigma. Okay. So we are done with this question. Now we'll go towards the next one. So it is observed that the total battery time for laptops of a particular brand is normally distributed with known standard, not distribution, standard deviation. So we have sigma to be 4. So here we know the standard deviation of the population. Okay, now for a random sample of 36 such laptops, so n is 36 here. The sample mean of the total battery times is obtained as 7. Now sample mean means we have x bar to be 7. Okay, now we know the standard deviation. We have this the sample mean we have. Now we need to find the 99% confidence interval for mu. Okay, so what will be the formula for that? As I have already mentioned, that when sigma square or sigma is known, we have confidence interval to be this x bar minus z alpha by 2 sigma by root n. So it will be, so confidence interval will be x bar minus z alpha by 2 sigma by root n to x bar plus z alpha by 2 sigma by root n. Now we need to find the 99% confidence interval. So alpha will be 0.01 and alpha by 2 will be 0.005. Okay, sigma we know, n we know, x bar we know. We only need to know the z alpha by 2. Now just consider this thing that alpha by 2 is 0.005. Now we need to calculate this z alpha by 2. We need to calculate. So now what z alpha by 2 actually is? So if I have this normal normal curve, then this point is called z alpha by 2 if the area here, this is alpha by 2. Okay, but so this area is alpha by 2. Okay, but we have this normal distribution table. Now this is a normal distribution table, standard normal distribution table. Here these areas are given from minus infinity to x. Means that in the table the areas are given, this areas are given, not this area is, this area is not given, these areas are given. So basically we have this. So what it is? So basically, if this is alpha by 2, so this will be 1 minus alpha by 2 because the whole area is 1. So this will be 1 minus alpha by 2. So what we need to find out, that integral minus infinity to z alpha by 2 fx theta dx. So this will be, so this area is 1 minus alpha by 2. We need to find this point such that this area is 1 minus alpha by 2. Okay, so 1 minus alpha by 2 is what? So 1 minus 0.005. So this will be 0.995. So we need to find this point in the table. So I am emphasizing on this thing because here, just like the t table, you cannot directly find out the value of the, because alpha by 2 is 0.005. So just find out 0.005 and write the value. No, that is not the case here, because here in the table the values are given from minus infinity to x. So these areas are from minus infinity to x, but we need to have this situation that, this area is alpha by 2. So we need to find out that what this area is actually. So if this area is alpha by 2, this area will be 1 minus alpha by 2. So we need to calculate such a point such that this area integral is 1 minus alpha by 2, that is 0.995. So area is 0.995. We need to find out this point. Okay, now we will be finding out it from the table. So the area is 0. Yeah.
Ma'am,
So
sorry
0.
to interrupt, ma'am. Can you explain this thing again, ma'am?
Okay, so I am saying that, okay, just write this, see this table. So in this table, what it is given? It is given these are the values of x. So these are the values of the point, and these are the values of the integral. So basically these are the areas and these are the point. Which point I'm talking about? So if here I have this standard normal curve, so what it is given, that this point is x, and so the area which here, these are given, so this is this area. So these areas are this areas. So these are the areas in the left hand side of this point. Such points are given. Okay, so these points, x is given here in the table such that the area in the left hand side is this. But in the question, we need to calculate. So this z alpha by 2 is the point, and we have the condition that in the right hand side, the area should be alpha by 2. So I cannot directly go there and find out, because here the areas are given in the right hand side of the point. So I need to find out that what if the the left hand side of the point. Now here I know that right hand side area is alpha by 2. So since the total area is 1, so the left hand side the area will be 1 minus alpha by 2. Now, so I need to, now from this table, I need to get this area in order to find out the point. So what it will be? It will be minus infinity to z alpha by 2, this integral of fx theta. So this is equals to 1 minus alpha by 2. So this I know because I know the alpha. So this is 0 point for that question. This is 0.995. Okay. Now here I need to calculate this point. Now I am talking about the area in the left hand side, which is given in this table. Okay, so in this table, the area on the left hand side of the point is given, but I have the situation that I know the area in the right hand side. So I need to convert my problem such that I have the area in the left hand side of z alpha by 2. I need to calculate the z alpha by 2 as that value. So it will be minus infinity to z alpha by 2. So that will be this area, 1 minus alpha by 2. So that will be 0.995. Is this clear?
Yes, ma'am. Thank you, ma'am.
Okay, so now we have 0.995. Just find out where 0.995 is here. So here we have 0.995 here, 9951. So this is the point 2.58. So this is the point 2.58. So z alpha by 2 will be 2.58. So it will be, so this implies, so which implies that z alpha by 2 is 2.58. Now we have all the values with us. So we have z alpha by 2, sigma n and x bar. So just calculate it. So it will be 7 minus, it will be 7 minus 2.58 into sigma. So sigma is 4 by root n. So sigma is 4, root n is root 36, so it will be 6, comma 7 plus 2.58 into 4 divided by 6. So what will be the confidence interval? Just calculate these values.
Five point 28,
5.28,
comma 8.72.
8.7. Right. So this will be the 99% confidence interval. So you just see the table where what are the areas are given, and be conscious about the finding out the values of this z alpha by 2. Because if the table is given in another way, then you can directly write the point. If the table is given like the area on the left hand sides are given, then you can directly find out that this will be that point. But if area is given in the left hand side, then you need to just calculate. You have this thing that z alpha by 2 is the point when the area in the right hand side is alpha by 2. You just keep this thing in mind and just modify it with respect to the table in whichever way it is given. Okay, so I hope this is clear. So I'll be moving forward towards the next question. Okay, so a manufacturing company produces bolts for various industrial applications. As part of quality control measures, the length of bolts is a critical parameter that must adhere to be specified standard. To ensure quality, a random sample of 16 volt is selected. So N we have as 16. So 16 volts are selected from the factory known to produce bolts with lengths from normal distribution. So now the lengths of the bolts are coming from the normal distribution. Now the observed sample mean of the of bolt length is 41.55. So this is basically the sample mean. So we have x bar to be 41.5 mm. Okay, and the sum of squares of deviations from the mean is calculated to be 135. So basically it is given that summation xi minus x bar whole square is given as 135. Okay, so this is given as 135. So s square will be 135 upon 15, because we have 1 upon n minus 1 summation. So this is very important. You just don't directly write that s square is 135. So it is given as sum of squares of the deviation from this mean is calculated to be 135 mm square. So s square will be 135 by 15. Okay. Now we need to find out the 95% confidence interval for the mean. Now we do not know the sigma square, and we need to find out the confidence interval for the mean. So what is the formula? So we do not know the sigma square, and we need to find out the mean. So we will be having this confidence interval. So this is, so the confidence interval, let me write. So 95% confidence interval for mu is, so it is x bar minus t alpha by 2 comma n minus 1 s by root n comma x bar plus t alpha by 2 comma n minus 1 s by root n. Now s square we know, so we can find out the value of s here. So this will be 27 by, so it will be 9 here. So s will be 3. Okay. Now s is 3, n is 16. S is 3, n is 16. X bar we already know. X bar we have 41.5. Now we need to calculate this t alpha by 2 comma n minus 1. Okay, now 95% confidence interval means alpha is 0.05. Okay, so alpha by 2 will be 0.025, and n minus 1 is, since we have n to be 16, so n minus 1 is 15. So we need to calculate t 0.025 comma 15. So we'll see the t distribution table. So that will be here. So we have degrees of freedom as 15 and alpha to be 0.025. So it will be this value, 2.131. Okay. So it is 2.131. Okay, now just place the values. So x bar is 41.5 minus 2.131 into what is S3 by root n, that is root 16, that will be 4. So it is 41.5 plus 2.131 into 3 by 4. Just calculate it.
$39.901,
Okay, 39.901,
43.098.
43.098.
098. 098.
Okay. Yeah, so this will be the 95% confidence interval for mu. Okay. So the main thing is to identify, first of all, what is the confidence interval, and in order to find out the confidence interval, we need these values. So which we will be finding out from the tables. Now for the next question. So a manufacturing company decided to ensuring the consistency of the thickness of metal sheets produced in its factories. Maintaining uniform thickness is critical to meet the required standards for product quality. Given that the standard deviation of certain measurement of metal sheet thickness is 19.3. So for the metal sheet thickness, the standard deviation is given. So the standard deviation sigma is given to be 19.3. What is the required sample size? So we need to find out the n from the normal population to assert with a probability of 0.95. So with a probability of 0.95, what is the assertion? So what that the sample mean will not deviate from the true mean. So basically sample mean and true mean, the deviation is given by this thing. So the sample mean will not deviate from true mean thickness by more than 3 mm. So the thickness should be less than equals to 3 mm. So it is saying that the sample mean and the true mean, the it will not should not deviate by more than 3 mm, means the deviation should be less than or equals to 3 mm. So this is the assertion, and what is the required sample size such that this assertion has probability 0.95. So basically this is the question. Now here we have x bar minus mu mod less than equals to 3. Now we know that x bar minus mu by sigma by root n follows standard normal 0, 1. So we'll just make that quantity here. So it will be probability of mod, and what is x bar here? Whatever it is. So x bar minus mu upon sigma by root n. We'll write it here like that. It is less than is equals to 3 upon sigma. So what will be this 19.3 by root n? So root n will go upward. So it will be root n here. So it is 0.95. So this is, we have this situation. So this is basically the standard normal. So it is z. So this is probability mod z less than is equals to 3 root n by 19.3, and this probability is 0.95. Now we can write it as minus 3 root n by 19.3 less than z less than is equals to 3 root n by 19.3. This is 0.95. Now this probability can be written as probability z less than is equals to 3 root n by 19.3 minus probability z less than is equals to minus 3 root n by 19.3. It is equals to 0.95. Now probability, since this is a symmetric distribution, so probability z less than is equals to minus 3 by root n by 19.3 is equal to probability z greater than is equals to 3 root n by 19.3. So we can write it as, which implies probability z less than is equals to 3 root n by 19.3 minus probability z greater than equals to 3 root n by 19.3 is equals to 0.9. Symmetric distribution properties we have already studied. So now this can be written as 1 minus probability z less than is equals to 3 root n. So it will be, this implies probability z less than is equals to 3 root n upon 19.3 minus probability, so minus 1. So it will be 1 minus probability z less than or equals to this quantity. So it will be minus 1 plus probability z less than or equals to 3 root n by 19.3 is equals to 0.95. So this 1 will go there. So it will be twice probability z less than is equals to what is that quantity? 3 root n by 19.3. So 3 root n by 19.3 is equals to 1 plus 0.95. So it will be 1.95. So it will be probability z less than is equals to 3 root n divided by 19.3 is equals to, so it will divide it. So it is to 0.975. So what we have this standard normal, and we have this point. This point is 3 root n upon 19.3, and the area which is less than this, so this area is given to us to be equals to 0.975. So since we in the table we already have these areas, so we'll directly find out the point. So this implies that 3 root n by 19.3 is what we'll find out from the table. So the area is 0.975. So area is 0.975 here. So in the normal table, the area is 0.975. So just find out where is 975. So this 0.975 is this, and the corresponding point is 1.96. So the point is 1.96. So this will be equals to 1.96. So under root n will be equals to 1.96 into 19.3 divided by 3. Just calculate it. What is it coming? Or just calculate the value of n. Just calculate the value of n. So it will be the square of this. So what is it coming out?
$158.9.
So it is coming out to be 150.
9.
158.9 it is coming. So we can write that n is approximately equals to 159. Okay. So this is the value of n. So here, because we have the left hand side area, that's why we have directly written the point. But in that case, in the previous one, we had this right hand side and we had that point. That's why we have to convert it into the area of the left hand side and find out the value from the table. Okay, so I will be moving forward from the next question. So a manufacturer of engineering components buy hydraulic seals for two suppliers. Sample are selected from among the seals obtained from these two suppliers. So we have two suppliers. Okay, let me name it as supplier 1 and supplier 2, and each seal is tested to determine the amount of pressure that it can withstand. Now, assuming that the withstand pressure of two machines is normally distributed, so the withstand pressure maybe X to be the pressure for uh, supplier 1 and Y to be pressure for supplier 2. Let us consider X and Y, and now we are considering them to be normally distributed. Okay, the population variances of the pressure are also known. So we know the population variances means sigma 1 square and sigma 2 square are known. Okay, from the past records, the results are shown. So here we have the sample sizes, we have the mean, okay, we have the variance. Okay, now find 95% confidence interval for, so basically it is a sample mean, okay, because uh, we need to find out the confidence interval for the difference of population means of the pressure produced by the machines. So we need to find out confidence interval for mu1 minus mu2 when sigma 1 square and sigma 2 square are known. So both of them are known and we need to find out the confidence interval for mu1 minus mu2. So let us see what is the confidence interval in that case. So for mu1 and mu2, mu1 minus mu2, if both are known, the confidence interval are given by these things. So this is x bar, y bar we know, we have from the table, and z alpha by 2 we need to calculate, and sigma 1 square, sigma 2 square we already have. Okay, so let us write all these things there. So sigma 1 square and sigma, so first of all let us write. So for that, let us consider this to be the number of samples. So this is for the machine 1 and this is for the second machine. So M is 36 for the first machine. So let me write this for machine 1. The random variable is x here. So M is 36. Okay. Sigma 1 square is what? Sigma 1 square is 0.01. 0.01, and x bar we have 13.50. Okay, now for machine 2, n will write, n is 36, they are same. Sigma 2 square we have 0.0025, and y bar is 13.38. So confidence interval for, or let me write first what is the value of alpha here also. So we need to find out 95% confidence interval. So alpha is 0.05 So alpha by 2 will be 0.025. So we need Z alpha by 2. Okay, so Z alpha by 2 is needed. So we already have calculated this Z 0.025 for that problem. So what it was? So Z 0.025. So this, okay, this was 0.005. Okay, we need to calculate 0.025. So okay, so this will be different. So we will be calculating it from the table. So okay, so uh, let me write it in the next one. So what we need to calculate basically? So we need to calculate. So we have this Z 0.025. So this implies that this area is 0.025. This area is 0.025. So which implies that this area is what? 1 minus 0.025. So we need to calculate the integral from minus infinity to 0.0, sorry, z 0.025 fx theta dx is equals to 1 minus, this is the area, so 0.025. So it will be 0.975. Okay, so now we will find out the value, this value in the standard normal table. So this implies Z 0.025 is equals to, so where the 0.975 is coming here. So 0.975 is coming at point 1.96. So as we have previously calculated, 1.96 then 0.975 is coming. So it will be 1.96. So we know now this Z alpha by 2 is also known. Now the confidence interval for, or I can say the 95% confidence interval for mu1 minus mu2 is given as, so it will be x bar minus y bar minus um, Z alpha by 2 under root of sigma 1 square by m plus sigma 2 square by n. Okay, comma x bar minus y bar plus Z alpha by 2 sigma 1 square by m plus sigma 2 square by n. Now we know all the values, so we will be substituting. So x bar minus y bar. So here x bar is 13.50, y bar is 13.38. So the difference will be 0.12. So x bar by y bar minus y bar is 0.12 minus z alpha by 2 is 1.96. Okay, now under root sigma 1 square, sigma 1 square is 0.01. So 0.01 by 36, it will be 0.01 by 36 plus 0.025 by 36. So, and let me write it in this way, plus minus, because we need to calculate this. Okay, so it will be, now what this quantity will be? So this quantity will be 0.12 plus minus 1.96 into, this will be this will add up to 0.10125 under root of and divided by 6, because this is in under root. So just calculate it, what is it coming, this quantity is coming out to be. So the confidence interval, so it will be 0.12 minus 1.96 under root of 0.0125 divided by 6 is point, and it is 0.12 plus 1.96 under root of 0.0125 divided by 6. So what it will be? So it will be, just cross check it, it is 0.0835 comma 0.1564. There may be a minor difference because of the taking of under root first and then dividing, or dividing then taking the under root. There may be a minor difference, but I think this will be the confidence interval. Is the 95% confidence interval for mu 1. So is it coming the same?
Yes, ma'am.
Okay. So we will be now moving forward for the next question. We are just applying the formula and just writing the value from the table. Okay. So in the question 8, we have from the lots of transparent polyester film sheets produced by two machines. Samples are taken from both the machines. So from the both the machines, we have taken the samples and thickness of the values of the film sheet. So thickness we have calculated in millimicrons are measured. Now the results are given below. So sample size, here it is sample mean basically. Okay. So sample mean and sample variances are given. So here we do not know, since the sample mean variances are given. So here we need to find a 99% confidence interval on the difference of the means. So we need to find out the 99% confidence interval for mu1 minus mu2 uh, of the thickness values of the film sheets from two machines, assuming that both the populations are having equal variances. So we do not know. So sigma 1 square and sigma 2 square are unknown but equal. But they are equal. So we need to consider this case. We have x bar, y bar, we have sigma s1 square, s2 square, we have m and n. We only need to calculate the confidence interval. Now, what is the confidence interval for this one? So when both are equal, the confidence interval will be this. So we need to calculate the pooled standard deviation SP, and we need to calculate these t values, t alpha by 2 m plus n minus 2. So we will be calculating them further. So first we will calculate the SP. Okay. So SP is what? So it is, let me write the values of m and n first. So for machine 1, okay, we have m is equals to, and we have s1 square is equals to, and what another thing we have, x bar is equals to. So we have sample size as 10, mean as 115, and s1 square as 25. Okay. For machine 2, we have m as 12, not m, n, it will be n here, n as 12, s2 square as s2 square is 9, and y bar we have 113. Okay. Now we need to calculate the SP square. So SP square will be m minus 1 s1 square plus n minus 1 s2 square divided by m plus n minus 2. So that this will be the SP square. So m minus 1 is 9, 9 into 25 plus this is 11 into 9 divided by, so it is not point, it is multiply, and this is m plus n minus 2, that will be 20. Okay, so this will be, so what this SP square will be, so it will be 9 into, now 25 and 11, so it will be 36 by 20, so it will be, so it will be this thing, and it will be
16.2, ma'am.
yeah. So SP will be what? It will be under root of 16.2. So it will be 4.02. Okay, now we know the SP. Now what we also need to know the T, the value of T alpha by 2 comma M plus N minus 2. So that is, now what is alpha? So here we need to calculate the 99%. So alpha is, so here only I will write that alpha is 0.01. So alpha by 2 will be 0.005. So it will be 0.005 comma m plus n by 2, 10 plus 12, 10 minus 20 it will be. Okay. So what will be the value of this? So we'll calculate it from, we'll see it from the table. So t 0.005, so this will be the alpha value, and the degrees of freedom was 20, so it will be 2.845. 2.845. Now we have all the values with us. Okay, now we'll write the confidence interval. Confidence interval for mu1 minus mu2, 95%, 99% confidence interval will be, so it is given as it is x bar minus y bar plus minus, I can write sp under root m plus n by mn into t alpha by 2 comma m plus n minus 2. So x bar minus y bar is 2 we have. So it is okay. I've done a mistake. So it is 112 here. So it will be 112 here. So the x bar y minus y bar will be 3 plus minus. What is SP? We have 4.02. So this is 4.02. What is this under root m plus n? Can calculate it here. M plus n by mn. So this is under root. So m is 10 and 12. So it will be 22 by 120. So this under root will come as 0.428. Okay. So this will be multiplied by 0.428 into 2.845. This will be the confidence interval. Now after the calculation, the confidence interval will come out to be 1.90 comma 7.90. So just cross check it. This is the 99% confidence interval for mu1 minus mu2. So we are done with this. This is for the mu1 minus mu2. Now we will move forward. So anybody has done the calculation? Is it coming out to be the same? Okay, just do it yourself and just cross check it whether it is same or not. So I'll be moving forward for the next question. So here we have a pharmaceutical company in conducting research to assess the variation in the effectiveness of two new drugs. So here we are interested in the variation in the population. So population 1 of the drug follows normal mu1 sigma 1 square, while population 2 is following normal mu2 sigma 2 square, okay, of the drug 2. Now the company aims to analyze the ratio of the variances. So we need to we are interested in the ratio of the variances between these drugs. Samples are drawn from both the population for testing with the sample size and sample variances. Now we know, so we have the sample size m and n. So here we have m to be equals to 25 and n to be equals to 21, and here sample variances are given, that is s1 square is 0.021 and s2 square is 0.01. It means the population variances are not known also, and we need to calculate the ratio, the confidence interval for the ratio. So let me see what is the formula for that. We have already written here. So here confidence interval for sigma 1 square and sigma 2 square, because both are unknown. We do not know what mu1 and mu2 are. So we are interested, we will be doing the things by using this. So s1 square by s2 square, f1 minus alpha by 2, n minus 1, m minus 1. We will be writing this. So it will be, the 95% confidence interval for sigma 1 square by sigma 2 square is, so it is S1 square by S2 square f of 1 minus alpha by 2 comma n minus 1 comma m minus 1. Just keep this thing in mind that first what is coming, the degrees of the second population, okay, and here at last it is coming the degrees of the first population. So this is important, this is important to remember. This is S1 square by S2 square f of alpha by 2 n minus 1 comma m minus 1. Okay, now we have all these values, we are more interested in this. So alpha is 0.05, so alpha by 2 will be 0.025, okay, and 1 minus alpha by 2 will be 0.975, okay. So these are the values we are interested. So f at alpha by 2 we need to know, and f at 1 minus alpha by 2 we need to know. Now for f distribution there are many tables, you can also find it online, but like I also have considered one of the table, but there may be possibility that only one of them is there. Like for alpha by 2, maybe for 0.025 it is given, but for 0.975 it is not given. So you can also find out the value by using the 0.025 values, because we know since I have here with me, I have table for 0.025. Okay, so I will be calculating this value by using this alpha by 2 only. So since I have this alpha by 2 with me, so I will be calculating, finding it out for this one. So f 0.025, n minus 1 is what? So n is 20, so it will be 20, 21, it is 20, so it will be 24. So I have this table with me. So it is given by this one. So here, let me zoom it first. So this is given for this 0.025, and from this table I need to find out, here the degrees of the numerator is there and this is the degree of the denominator. So I have n minus 1 to be 20. So 20 is here, this is 20, and this is here in the denominator I have 24. So this is 24. So the value is 2.373. So maybe there is like you may not be able to see the correct value because it is a very like, it is like 2.3273. Okay, so I will be using this value. This is 2.3273. So this is 2.3273. But I do not have the table for the another one. If I do not have the table, I can directly calculate by using this value, because we know that f of 0.025, 20 comma 24, so this will be equals to 1 upon f of, so we know the relation that f of alpha m comma n is equals to 1 upon f of 1 minus alpha n comma m. So by that relation, so 1 minus alpha will be 0.975, and this will be 24 and 20. This will get exchanged. So this value from the table, if I will calculate, so this is, so 0. I'm sorry. So I need to calculate this for 975. I need to calculate it for 0.025 I've already calculated, so it will be 975. So it will be what? So it will be 1 minus alpha. So 1 minus this quantity. So 1 minus this quantity will be 0.025. And I have the table for 0.025. So 24 and 20 are getting exchanged. So we have now 24 at the numerator and 20 at the denominator. Denominator 20. So the value, the corresponding value will be this. So this is 2.4076. Okay. So this will be 1 upon 2.4076. I just divide it by 1, then we will be having this 0.5 of 0.975, 24 comma 20. So it will be 1 upon are 2.3273. Okay. Yeah, so it will be, yeah, so it is 1 upon, so 1 upon 2.4076. So 1 upon 2.476. So it will come out to be 0.4153. Okay. So this way, if you have only one table available, if you have for both the alphas, then there is no problem. If you have availability of only one table, then you will calculate this by using this value. Okay, by this relation. So so it will be that, and now we will put the values here. So it will be, confidence interval will be, so s1 square by s2 square. So it will be, s1 square is 0.021, 0.021 on 0.018 f1 minus alpha by 2 n minus 1 m minus 1. So this is this value. So this value is what? 0.4153, comma 0.021 divided by 0.018 into, so this is the value, we have 2.3273. 273. So, so the confidence interval we will be getting is 0.484, 2.715. So the main role here was the how to calculate this f values if there is availability only, if there is availability of only one table. Okay. So I hope this is clear.
Yes, ma'am.
Okay. So let me see this next question also. So our research team is studying the effectiveness of a new teaching method on student performance in mathematics. The team plans to collect data on the average test scores of students using new method and analyze the variance in performance. Assuming a normal population of test scores with a variance sigma square is equals to 6. So sigma square is 6 here. Find the probability that a random sample of 25 students. So we need to find the probability here, n is 25, exposed to new teaching method will have a sample variance between this. So basically we need to find out the probability that a sample variance, which is s square, is between 10.745 and 3.462. We need to find this probability. Now directly we do not know what is the distribution of s square, but we know that n minus 1 s square by sigma square follows chi square with n minus 1 degrees of freedom. Okay, so so we'll convert this into chi square. So this is probability. So here uh, we'll multiply by n minus 1, which is 24, and divided by 6. So this is 3.462 into 24 divided by 6 is less than is equals to, now this is chi square with 24 degrees of freedom. So it is 24 by 6 into, what is the value? That is 10.745. 10.745. So this will be cancelled out. This will also be cancelled out. So it will be probability. So the product will be 13.848 less than is equals to chi square with 24 degrees of freedom less than is equals to 2.71, not 42.98. Now you need to find out this value. Okay, so this is, so now let me so this is basically the chi-square distribution. Okay, now this point is, let us consider that this point is 13.848. Now this point is 42.98. Okay, we need to calculate this area. Okay, so what is this area basically? I can write this area. So this is probability is written basically this area. So this area can also be written as probability of chi square less than is equals to so we can write it as probability chi square less than is equals to 42.98. No, basically this area. So this area minus this area. Okay, or I can write it as probability chi square greater than is equals to this minus greater than equals to this. Okay, so I will write it as probability chi square 24 greater than is equals to, so this area whole, this area. So this is greater than equals to 13.848. Now this whole area minus probability chi square 24 greater than is equals to 42.98. Now why I am taking this greater than quantity? Because in the table this quantity, the area of these quantities, the probability of this quantity is given. So area, the right hand area is given in the table. So that's why I am taking the right hand side. So this will be from the table. So this is chi square greater than 13.848. So this is chi-square distribution 24 degrees of freedom. Now where the 13.418 is appearing, so since the nearest value for 13.4 it is there, the nearest value is this only, so we'll consider this point. So it will be 24, so the area will be 0.95 here. Okay, so here it is 0.95 minus, here it is the point 42.98. So here 42.98 is here for the 24 degrees of freedom. This is the 42.98 and the area is 0.01. So here it will be the 0.01. So it will be 0.94. So basically the probability that this probability that s square is between this these two values, the probability is 0.94. So is this okay? Why we have not taken the less than quantity? Because we do not know. Because in the table these the area on the right hand side is given. That's why I am taking the right hand side probability. So yeah, I will be stopping here. If there is any doubt or anything, then you may ask. Also, I want to let you know that there will be an extra session, most probably on Sunday from 11 to 1. So you will be getting information before one day. So probably there will be a lecture. So if you want to attend, then make yourself free on that day. So it is on Sunday, 11 to 1. I'm not sure about it, but most probably it will be there. Okay. Now, if there is any doubt or anything, you may ask. Otherwise, I will be ending this session. Okay, thank you guys. So, okay, if there is any doubt, then I will end this meeting. Thank you, all of
Thank you,
you.
ma'am.